Good evening, everyone, and welcome to the 2022 Cierva Lecture, which has been, it's fair to say, some period in gestation, given the slight global hiatus we've had over the last couple of years. So it's a real delight to be here in person, and delight so many of you could join us. And it falls to me. I'm Nick Leven. I'm Professor of Aircraft Dynamics, Rotorcraft at the University of Bristol. And I'll do, I won't be grand here, the top and tailing of the lecture. So I know it falls to me to do the dullest part, which is the housekeeping, so just bear with me for a minute. It does get better from that point. There's no fire alarm test planned. If the alarm sounds, please exit the building. The Society's designated assembly point is the paved and railed area at the junction of Hamilton Place and Piccadilly, beyond the Intercontinental Hotel. If you have mobility or access issues, please make yourself known to a member of staff at the event. I hope that's okay, because you're now in here. And they will help you if you need to leave the building. Do not leave unmarked bags or other items unattended. And as a courtesy, please could you switch your phones to silent during the talk. The event is being recorded and will be available to you and others on YouTube subsequently. We will have questions at the end, time permitting. And we'll have a roving microphone, so if you do want to ask a question, please do it to the microphone, because otherwise we can't record it. The lecture is planned to end at 7 o'clock. And so now I've done, as I say, things improve from this point onwards. So it's my great pleasure to welcome Farhan Gandhi to the UK. He arrived this morning from the US, so we need to treat him nicely. As I say, we've probably been discussing this lecture for 3 years, on and off, so it is a real pleasure to welcome him in person to the Society. And just something about Cierva, to put it in context. Cierva, as attributed of having invented the autogyro, so novel rotors. And that is the topic of what Farhan is going to talk about this evening. We live in a very exciting world in rotorcraft at the moment, with the development of eVTOLs, new configurations. Actually, Farhan has lived and breathed this for certainly the last 20 years of his career. So I'm genuinely excited to hear what he's got to say. So a few details. I will not read you all 40 pages of his CV, but here are a few highlights. He graduated from IIT Bombay, the bachelor's in Aerospace, and then went to University of Maryland, did his PhD with Inderjit Chopra, who also knows quite a lot about rotorcraft. Then went to Penn State for 16 years and went through the ranks, becoming a full professor there, and subsequently moved to Rensselaer Polytechnic Institute, where he is at the moment, and is director of the Center for Mobility with Vertical Lift, or MOVE. But what distinguishes Farhan is not just academic work. He has worked with an extensive range of industries, not least all three of the armed services in the US, DARPA, NASA, Boeing, Sikorsky, Bell, United Technologies, GE. So he is fully aware of what the industrial challenges are. And also he's worked more locally with Augusta Westland Helicopters when he was here as on a fellowship at the University of Bristol. Clearly the highlight of your career. But actually, it's interesting that it's quite nice that it's come full circle, that this event is sponsored by Leonardo Helicopters. I'm very grateful for that. And it's nice that actually Leonardo can hear what you've developed since you worked with them probably 15 years ago now. So I would like, it's a real privilege to have Farhan over from the States. I've been looking forward to this, as I say, for 3 years. So you're extremely welcome, Farhan. The floor is yours. Welcome.
I'd like to first and foremost thank the Royal Aeronautical Society for this wonderful opportunity. Any lecture that bears the name of Cierva, he's one of the pioneers of our field, it's a huge honor, and I'm very moved to have this wonderful opportunity. I'd like to thank Nick for working with me for the past so many years. You know, things were put on pause because of COVID and all the travel restrictions, but I'm extremely excited to be here. So I'd like to tell you, to talk a little bit about the subject of reconfigurable vertical lift. It's going to be a little bit of a whirlwind tour. So, you know, there's about 15 years or more of work with a number of journal papers behind all of this. And what you'll see is a lot of papers boiling down to one chart. But I want to share and expose ideas that I think are very exciting. So what is morphing? Morphing is basically the change of shape or the change of form. You know, if you think about a retractable landing gear, you can think of that as morphing. The nose droop on the Concorde was morphing. People in the fixed wing world tell me that you rotary wing guys are doing morphing now. We've been doing it for a long time, but the tilt rotor aircraft is actually a morphing aircraft, right? It changes its form. So in the rotary wing world versus a fixed wing world, the challenges we face are much greater. And the greater challenges are kind of summarized here. One is the morphing structure on a rotor needs to withstand not just aerodynamic loads like you would have for a fixed wing, but it also has to withstand all the CF loads. So near the tip of the rotor blade, the CF, the centrifugal accelerations, close to 1,000 G. And the morphing structure and the actuator system has to be able to withstand those kinds of loads. So, you know, to have something that is simultaneously deformable and at the same time stiff enough to withstand load is a challenge. Compared to a fixed-wing aircraft, the space restrictions on a blade of a rotor are far stricter, so you're working in a very small space. And the other final, what I would call big challenge is the transfer of power from the non-rotating to the rotating system. So, you know, that could be electric power, it could be hydraulic power, it could be pneumatic power, usually done through a slip ring. And in a lab environment or, you know, in a wind tunnel, it works and you get the test done and you show your results, right? But in an operational environment which is harsh with sand and ice and, you know, moisture and such, the longevity of such systems becomes a challenge. So I want to talk a little bit about morphing classification and general categorization. In the fixed wing world, they use terms like gross morphing and fine morphing. So what is gross morphing? Large things. If you change the sweep of a wing, that's gross morphing. If you're trying to change the span, you know, big things, right? It's gross morphing. Smaller, like camber of an airfoil or, you know, slight nose droop, those kinds of things, the fixed wing community thinks of as fine morphing, smaller. But in the helicopter world, the distinction is typically based on frequency. If you're doing high frequency, low amplitude kind of changes, that is basically active rotor control. And that's been done for a long time for vibration reduction, noise reduction, you know, a couple of degrees of twist or a few degrees of flap deflection. Rotor morphing generally refers to higher amplitude, generally quasi-static deformation. It could be low frequency 1 per ev, but generally larger shape changes. Not so much for vibration and noise, but for other reasons that we will talk about. So morphing, by morphing rotors, we typically refer to rotor blades that may change, say, the chord, may change the twist or the camber, change the span, change the airfoil shape. And if you're able to do all of that, what are the benefits that it will give us? First, it can give you optimal performance in diverse operating conditions, right? Because typically, if you look at the optimal geometry when you want to hover or when you want to be in very high-speed flight, they can be different. So if you have a fixed geometry rotor, it's either optimally designed for one condition and can perform poorly elsewhere, or it's a compromise solution that doesn't do very badly anywhere, but doesn't do very well anywhere either. So the ability to change configuration would give you optimal performance at diverse conditions. So, you're not dealing with a compromised design. Of course, you always have to think about a cost-benefit analysis, that you're doing that, but does the benefit that it give you outweigh the cost, right? So that's important. The other thing you can get with morphing is expansion of the operating envelope. So you may be able to fly higher, hotter, heavier, expand the stall boundary. You can increase the maximum speed. This is something that's of very high interest to the U.S. Army right now. They're working on the Future Vertical Lift program, and it also, morphing has the possibility, there is the possibility to get increased operational flexibility. So I'm going to dive into different types of morphing, okay? So let's start with chord extension morphing. Now, if you think of chord extension, I can extend the chord in two ways. One, I can have an elastic structural deformation, right? So I can have some substructure that deforms, maybe some skin that deforms or slides, or I can have effective chord increase through discrete shape change. So for example, if you look at these top figures here, what we have is a slit trailing edge and an extensible trailing edge plate. So you look at it and you might say that, well, an optimal airfoil performs very well. It gives you very high lift over drag, right? Now you have this optimal airfoil, and you've ruined its shape by sticking out a plate. The fact is that when you do it, it doesn't do that badly. It doesn't do that poorly, and it gives you the big thing that you're looking for, which is the increase in the solidity of the rotor, or more blade area. And this is something you can do rather easily as compared to elastically deform a structure to significant extents. So there are different ways you can achieve a particular goal. Now, when you think about chord extension, when do you typically want to use it? You typically want to use chord extension at the stall boundary, right? Because normally when you have a certain chord, and now let's say you're near stall, you're flying hot, you're flying heavy, you're flying high, the first thing you're going to do is you're going to increase pitch and try to generate more lift, to compensate for, say, density reduction. And then you can do it no more because of flow separation or stall. That's when chord extension will really help you. So in a way of speaking, chord extension is a high lift device, right? So if you're going to be using a high lift device, you should then compare it with other high lift devices, right? So one example of a high lift device is basically a gurney flap. A gurney flap is a small device that comes out perpendicular to the lower surface, and it can be right at the trailing edge, or maybe around 85-90% chord, and it can be either fixed or it can be retractable, and it can be deployed. So a gurney flap increases the max lift coefficient. However, if you look at CL versus CD, right? And if you look at a gurney flap, so the blue curve here that you see is for a baseline airfoil. So this is for a baseline airfoil, and this red curve that you see is with a 2% chord gurney flap. So you get this increase in maximum lift coefficient, but see what happens to the drag, right? So at low CL, where you don't need the gurney flap, then you're paying a very high drag penalty. On the other hand, if you look at this extendable trailing edge plate, this is the same airfoil in black, and in blue, what you have is the extensible trailing edge plate. So at high, what you've done is you've effectively increased the maximum lift coefficient by increasing the chord of the airfoil, but you don't pay this drag penalty at low CL. So that's the advantage of doing something like using an extensible trailing edge plate as opposed to a gunny flap. Now you can also get a higher CL max by drooping the nose of the airfoil. Okay, so here is a picture that shows that. But you see, the nose of the airfoil is a region where you have very high pressure, right? So fundamentally, you have to design the structure to be very rigid there. And if you're trying to take a rigid structure and ask it to deform, the challenge there is much greater than asking a structure that doesn't have to be that rigid to deform. So in the trailing edge region, obviously the pressures are much lower than the nose of the airfoil. So if you can get the outcome you're looking for, that is a higher CL max, right? By making changes at the trailing edge, that will be a better solution for you than to try to do the same thing at the nose of the airfoil. Okay, so I kind of covered this without hitting the bullets. So in the next slide, what I want to show is the kind of performance benefits that you'll get. So here are some simulations for a UH-60A Black Hawk helicopter. This is at 130 knots. And what I'm showing is power on the y-axis versus gross weight on the x-axis. And what I have here is pairs of curves. So the blue and the green curve together form a pair. And there are three pairs here. This pair here is at 4,000 feet. This pair here is at 8,000 feet, and this is at 12,000 feet. So let's take one pair. Let's take this pair here at the lowest altitude. The curve in blue represents the baseline aircraft. And this pull-up that you see is really that is a representation of stall, because what it's telling you is, you're consuming more and more and more and more power, but you're not able to generate any more lift, right? That's why this curve is starting to pull up. If you have an extensible trailing edge plate, so on the Black Hawk from 63 to 83% span, so 20% span, we have a plate that extends about 20% chord, and it comes down at a 2-degree angle compared to the chord line. If you have that, then you'll move from this blue curve to this green curve. Okay? And that happens at any altitude. So if you want to look at this pair of curves, you can look at it in two ways. Supposing I drop from the point A to B, right? Which says if there is no increase in gross weight, I get something like a 14% reduction in power close to the stall boundary. If I move in the horizontal direction here, so at the same power, if I move here, what I get is about a 1,300-pound increase in maximum gross weight. So, for a 20,000-pound aircraft, you can see that that's a significant percentage. So those are the kinds of performance benefits you get with with chord extension morphing and the stall alleviation that you're doing. Similarly, what you'll find is here you have power on the y-axis versus airspeed on the x-axis, and this is again for a Black Hawk. It's in high heavy conditions, so 8,000 feet, 22,000 pounds, which is a high gross weight for this aircraft. And the blue curve is the curve for the baseline aircraft, and the green curve is the curve when you have chord extension. So in the power bucket, you'll get a small reduction in power requirement, around a 4.3%. But here, what you'll get is around close to an 18 to 20 increase in max speed, and at high speeds, you'll get a greater reduction in power. Now, so the question then is, why not have a fixed large chord? Why do I need to morph it, right? Because all the benefits I've shown you are close to stall. When you're flying high, when you're flying hot, when you're flying heavy, right? So here, if you look at power versus gross weight, and this black is the baseline curve, my extensible trailing edge plate is falling lower, so you can see the power requirements are lower, right? This is at 90 knots, this is at 8,000 feet, and here on this part of the curve, I'm looking at high gross weights. But what if I go to lower gross weights, right? So if I look at this part from 14,000 pounds to say around, even if it goes up, but now at sea level, So I'm not at high conditions where the density is low. And when the density is low, I'm flying at high pitch, so I'm closer to stall, right? Here, what happens is a larger chord gives me a larger profile drag. And that increase in profile drag is giving me this 4% power penalty. So the point is this, that I'm going to be operating most of the time in benign conditions. I think I'm not going to be operating all the time at the edge of the envelope, right? So if I try to give myself high chord to hit those points where I may be flying some small percentage of the time, I don't want to pay this 4% power penalty all the time, the 95% of the time when I'm not at the stall boundary. So that's the benefit of morphing, that you use it when you need it, and when you don't need it, you gain by not having to pay this power penalty. Okay, so likewise, if you look at here in this particular chart, what I'm showing is some levels of vibration. So again, this is for the Black Hawk at 90 knots. This is at 8,000 feet. We have on the x-axis gross weight. So it's increasing gross weight. And on the y-axis, you have the 4P vibratory hub loads. So here, the leftmost plot is vertical shear. This is in-plane shear, so combination of Fx and Fy. This is in-plane moments, so combination of pitching and rolling moments. And you can see that the baseline aircraft without chord extension, these are the blue curves. And when you have chord extension morphing, you fall to the green curve. So you can see 47%, 30%, 50% reduction in vibrations. Why do you have reduction in vibrations? Because the baseline aircraft was in deep stall conditions, and stall is not great for the rotor. Once you start pulling away from stall, you have better aerodynamics, which is improving the loads. So if you look at the combination of what chord extension morphing can do for you near the stall boundary, you can get 1,300 to 1,400 pounds increase in gross weight, close to 20 knots increase in max speed, about 12 to 14% reduction in power, plus this kind of 30 to 50% reduction in vibratory loads. So I'm going to move on and show you some hardware. We built some test prototypes, and we tested it in a hover stand. So in the top figure, what I'll show you is a video. So this has been tested at 375 RPM. It's about 48% full-scale CF loads. And here we've done this with pneumatic and use electromechanical actuators. So this particular test, it's on a paddle. We have a boom and paddle. It's about a 7-foot radius, and you can see this video looks stationary, but it's actually rotating. And the strobe light has been synchronized with the rotational speed, but you can see that in the presence of the rotation, the EMA, the electromechanical actuator, is able to produce an increase in the chord here. Okay. Then the other thing we did is we said, what if we did not use an electromechanical or pneumatic actuator, a discrete actuator, and instead use the centrifugal force, or the change in centrifugal force? So in the second prototype, what you see is we have here a device called a von Mises truss. And the way a von Mises truss works is if you apply a load at the vertex, it eventually deforms, and it can snap. And when it snaps, it goes from position A to position B. So now imagine if I connect through a link an extensible trailing edge plate to the vertex, then when the von Mises truss is kind of retracted into the airfoil, the plate is retracted into the airfoil, and when the von Mises truss deforms and goes this way, the plate will get pushed out, and I will get a net increase in chord. So here, what you see happening is that the centrifugal force is predominantly acting along the span-wise direction, but not entirely. There's also a chord-wise component, depending on the CG distribution and such. So the chord-wise component of the centrifugal force, as this RPM increases, is going to keep increasing, and there will come a point beyond which it will pull the system out, right? Now, the thing is, how do you pull it back in? Because in that case, to push it back in, the force has to reverse, and the centrifugal force, when you slow down the rotor, becomes smaller, right? But it doesn't reverse. So to bring the plate back in, what we have is a retraction spring. So if you look at this entire system, again, this is a test at 450 RPM, and you can start to see the strobe light is going to be synchronized with the rotor. So it will look stationary, and you'll see the cord deploying. So as the RPM is increased, this deploys. And then when the RPM decreases, it's going to start to retract. So this is done without any actuators on the blade. This is done simply by changing the RPM. All right, so I'm going to move to the next type of morphing, which is rotor twist and camber morphing. So all modern helicopters basically have a negative twist, right? Washout. And typically that is there on the blades to reduce induced power in hover and at low speeds. So in high-speed flight, this washout creates a lot of problem because you can get a lot of negative lift on the advancing blade tip, and it can create vibration and performance losses and so on, produces a larger loads. So with the higher maximum speeds that are currently being sought for the future vertical lift program, they're looking for speeds in the regime of 200 to 240 knots. The large quasi-static blade twist variation would actually be very attractive to have on these edgewise rotors. It's also large quasi-static twist variation would also be attractive for tilt rotor aircraft, where you need, maybe about 10 to 12 degrees for hover, but when you get the rotors in propeller mode, what you would like is 45 degrees or 60 degrees, right? So how do you bridge that gap? So we did some work on variable twist over here. So if you look at this rotor at the top, this is a 4-foot section prototype. It's not tested in a rotating environment. It's tested on the bench top. You can see a significant amount of twist. So how was this done? If you think of twisting, right? If you can twist a closed cross section or you can twist an open cross section. And if you twist an open cross section, the twisting will be accompanied by warping. So in this particular prototype, this trailing edge was slit, and we were introducing warping of the top skin relative to the bottom skin, and the reverse effect was being used. So we were getting the twisting of the blade. And really, there was a cylindrical spar and a number of ribs around the spar that rotated. As you might imagine, you get a lot of twists, 16 degrees, but it's not a very flight-worthy system, right? Because you lost your primary load-bearing member, which was a spar. So in the bottom, what we did was we are not twisting this system. We've again used the same effect where we try to use warping, and what we have induced is camber. So what we have done in this case is we've taken a CH-46 blade, a section of it actually, and we have left the spar, which is a primary load-bearing member, untouched. Okay, so that carries the bending loads, flap-wise, chord-wise bending, a large amount of the torsion load. This blade is, what you're seeing here is a lower surface, and the skin has been slit just aft of the trailing edge, just aft of the spar. And again, there's an actuator here that's warping it, and you can see that, and there's a linkage. So as there is span-wise motion of that skin, there's also chord-wise motion, and the combination of those motions actually results in the camber of the airfoil. Now, camber of the blade. Now, camber is aerodynamically similar to twist. And let's think about why that would be the case. So if you think about lift on a blade, okay? Here is a blade, and I'm going to introduce camber over the inner half, or here I'm going to introduce camber. It's a span-wise variation in camber over the entire blade. And what I'm going to show here on these two lower plots is lift distribution versus span. So the solid line is the baseline blade, and then the dashed line is when I have this kind of inboard camber, Okay, so the left figure shows when I have this camber over half the blade, and the right figure shows when I have camber over the full span. So what is it doing? When you have camber and you go from the solid line to the dashed line, what you've effectively done is reduced lift outboard and you've moved lift inboard. Okay? When you negatively twist the blade, you're doing exactly the same thing. You're redistributing lift. So instead of getting a very high peak near the tip of the blade, you're starting to move lift inboard, which is what is making the rotor more efficient. So you can effectively do the same thing by camber, but you can do it at a lower price in terms of safety and in terms of load-bearing capability of the rotor. Okay, I have some results here which show the equivalence of camber and chord, but let me, in the interest of time, just move forward and move to the next concept of morphing, which is centrifugal force actuated variable span rotor. So this was some work that we did a long time ago, but here's the basic idea that supposing I had a rotor blade which was telescoping, and I had an inner fixed part and I had an outer sliding part, and there was a spring restraint between the two. So at low RPM, low speeds or no speed, right, the rotor would be compact, but as the rotor starts to spin faster and faster, the centrifugal force on this outer sliding part becomes greater and it overcomes the spring stiffness and starts to extend. So that's the fundamental idea here. And again, the beauty of something like this is that there's no actuation use. You're simply using the change in RPM. So here is a prototype that we built and we demonstrated it. So I'll show you a video. This prototype, you have the telescoping blade and there's a piece of tape. On the white part is on the fixed inner portion, and the blue part of tape is at the root end of the outer sliding portion. By the way, the rotor is spinning a lot faster than it appears over here. So you'll see that as the RPM starts to increase further, the white and the blue tapes move further apart, which is showing you that the rotor span is increasing. For this particular prototype, that increase in span was about 20%. So of course, you can ask the question that do I want my entire blade, or not entire, half the mass of the blade, or some significant portion being moving in that way, that kind of a dynamic system. If you were concerned with risk reduction, one of the things that you could do is you could think of an extensible tip, where you have a much smaller part of the blade that's effectively moving, and you're still getting an effective increase in span. Okay, so this year is the idea of the von Mises truss has now been flipped, and instead of using it for chord extension, by the way, this is really a half von Mises truss, and you can have the spring over here at the root of the truss, or you can have it in this link. And again, you can think of this system where as a centrifugal force on this blue portion increases, this link will get pulled outward and it will become vertical when the spring will compress, and then it will extend, and then it will move to this position and this blue part will slide out. So we actually built a little model of that, and we tried to test it on a small, maybe 1.5 foot type a model. And the thing we found is that one side deployed before the other side. So, because there are differences in friction there, so what we did is we came up with a cable system that connected the two so that one could not deploy without the other. They had to deploy together. And when we did that, things worked well. So this is RPM on the x-axis, and you can see the blade span-wise displacement. So, it increases, it increases, it increases, it increases, and then it snaps, right? And when it snaps, you get a significant increase in span. And then, of course, there's a maximum allowed displacement where we have a lock, so it's not going to increase any further beyond that. So you can see that the symbols, which is our test data, compare very well with our model predictions. And this is, I'm going to start this video. It's at 850 RPM, and it goes up. And you can start to see this whole little system. It's not a blade, it's just a model, but you can see the von Mises trusses expand, and both the sides of the blade expand together. Okay. And we have similar videos in a different view. So I'll just pass through that. Here are some performance results. I'm going to skip this slide, but I'll talk about this one. One of the things you can do is you can think about the benefits of geometric change and operational speed together, okay? So, can I change my RPM? Yes, and I can change it relatively easily. It's easier to change RPM. There are other challenges like vibrations and different resonances and such, but it's easier to change RPM than to change span or to change chord, right? But let's see what I can do with just one of them and what I can do with the two together. So this plot on the bottom left shows a UH-60A at 80 knots cruise, and this is 18,300 pounds gross weight. What I'm showing on the x-axis is the radius of the blade, and on the y-axis I'm showing the RPM. And this point here is the operating condition of the actual rotor. Okay, so basically these colors here show power levels. So red means high power and blue means low power. I would like to be generating this 18,300 pounds at the lowest possible power. So at this particular condition, if I move down here, I can get about 100 HP reduction, horsepower reduction, just by changing RPM. I don't need to change span. Okay, but let's see what happens when I go to a very high gross weight. Okay, so this is 24,000 pounds. Again, this here would be the nominal aircraft, its radius, and its operating speed. I cannot reduce RPM. If I reduce RPM, what's going to happen is I'm going to hit stall, right? So now what happens is that way, if I reduce only RPM, I'll get a max of maybe about 50 horsepower reduction. However, if I'm able to reduce RPM and simultaneously increase span, I can get about 150 horsepower. So you have to think about, what is your objective and what is the easiest way to reach that objective. When I can do it with RPM alone, I would always do that. But when the combination of RPM and some other geometry change gives me greater benefit, then that's when I would consider the morphing of the blade. Okay, so this span extension looks like a very high-risk thing, right? But, the companies, the OEMs have waded in those waters as well. So this is Boeing. Boeing worked on a project which was known as the disc rotor project, where essentially what they were doing was they were saying they would have these extended blades in low-speed hover conditions, and then in high-speed conditions, they would retract these blades into the rotor, into the hub over here, and then you would have wing-borne lift. So in the disc rotor project, of course, this was not centrifugally actuated. It was all they used actuators. And Sikorsky similarly worked on the variable diameter tilt rotor, where again they had actuators to have these larger rotors in the in the lifting condition, and then the rotors become smaller when they're propellers. Okay. So now one of the other morphing type changes that we looked at was this reversible airfoil. So let me give you a little history here. Boeing had something called the X-50 Dragonfly program. So this is a canard rotor wing. And what they had was a two-bladed rotor over here. And you can see that, if you think of the leading edge, the idea was that it would be a rotor in low-speed conditions. And in high-speed conditions, it would just stop and it would be a fixed wing. Okay, so the problem is this, that if you use a normal airfoil, and let's say this red part is the leading edge, you have the leading edge over here, and you have the leading edge over here, right? So as a rotor, it's working well for you, but when you stop it, what do you have? You have one of these sides of the wing essentially in reverse flow, right? So Boeing's solution to that problem was to use an elliptical airfoil. The problem with the elliptical airfoil is it does neither very well in hover nor does it do well in cruise. So one of the things that we did was we asked that can we reverse the airfoil? So we came up with a mechanism that actually does that, and the idea would be that you would have half the wing where you can actually flip the leading edge to the trailing edge. So here are some related slides. The prototype that we created used straight links. And when you use straight links, if you look at the pressure distribution, you're going to get these spikes because your airfoil surface is piecewise continuous. Well, in terms of slope, you have piecewise continuity, right? But if you use curved links, then you can get rid of that problem and you'll go to this green curve for the pressure. So you can improve the design. And what I showed was for a symmetric airfoil, but you can also design the linkage system such that the top half and the bottom half is different. So you can get this kind of airfoil reversal even for a cambered airfoil. Okay. So one other concept we worked on was wing folding. So why would you want to fold the wing? If you think of a high-speed compound helicopter, where you have the rotor doing the primary work in hover and low speeds, but at high speed, you have these wings, right? So at low speed, you get a lot of downwash from the rotor onto the wing, and you get these down loads. So we asked the question that, can we get the wing out of the way? So my solution was actually to have a retractable wing, but the students who were charged to work on this problem came up with a different solution. And their solution was actually a folding wing. And I thought to myself, how innovative, right? So when you're working with good engineers, you don't tell them what the solution is. You tell them what the problem is and let them come up with a solution. So their idea was, how about we tilt the wing parallel to the fuselage when you're in low speed, and then in high speed it starts to come out. So this is the concept, and then we built a prototype that kind of does that. So this is the frame of the wing without the skin, but you can see that we have an actuator, one that deforms the wing, and then there's another one that locks it in place. But this is the wing in its deployed condition. You started from the retracted condition. Okay, so let's move on to this idea of autonomous rotor morphing. You know, I started with morphing many, many years ago, and more of late I've been putting more energy and more effort into this idea of autonomous shape change. So can we use the change in operating conditions to affect the desired shape change? So that alleviates the need for complex actuation, it alleviates the need for power transfer, etc. And we already saw some examples of that. We saw rotor span change and chord change realized with RPM. There are also other things you can do. You can use RPM change to realize change in blade twist. You can use RPM change for blade folding and unfolding. And then I'm also, of late, I've been very interested in temperature change. Can temperature change be used for cambering an airfoil? And can we use aerodynamic pressure change to morph an airfoil? Okay, so I'm just going to expose you to some ideas here. So here is a change in RPM, which changes the centrifugal force. Here's the idea. And then if you have a blade that has extension twist coupling, right, as the centrifugal force changes, if the blade has extension twist coupling, its twist will change. The problem or the challenge that you're dealing with here is the following. Supposing I start with a UH-60-like blade. I have to build it in this way. I have to build it along this pink line. So I'm building it nose up, okay? And then when I'm at 100% RPM, the extension twist coupling, the large CF force at 100% RPM starts to twist it down, 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 and I go to this black line over here. The green line is the actual UH-60 twist, and the black line is like an idealized equivalent twist, okay? And then when I reduce the RPM to say 80%, which is where I might want to be in a high-speed compound version of the UH-60. So if I'm operating at 200, 220, 225, 230 knots, maybe I'll reduce the RPM to 80%. I would like it to be untwisted, but I can deal with maybe 4, 5 degrees twist. I don't want 12, 14, 15 degrees twist. So I'm going to come to this red line then. So you see at 80% RPM, I'm going to be at the red line. At 100% RPM, I'm going to be at this black line. This is the change in twist that I want, right? But I had to build the blade here. So now the strain that my structure has to tolerate is a change that goes from this pink line to the black line. So this is one of the challenges, the high strain and the structure when you try to use autonomous shape change for twist here. So in terms of autonomous shape change, this is another thing that I found very interesting. This was work done by NASA, and they're using RPM change to actually, I'm going to play this video. This is a NASA video.
There's some springs on the bottom as these spin down and slow. They self-stow against this.
Okay, so I'll play it one more time.
There's some springs on the bottom as these spin down and slow. They self-stow against this.
It's just a spring-restrained blade that, when the centrifugal force acts, it unfurls and it acts as a propeller. But when you're not spinning that motor, the whole thing kind of becomes compact. And this was on this aircraft over here. And you can see that basically at low speeds, all these props were operational because they were trying to use a rotor-blown wing effect. But at high speed, you only had these tip props, which were providing the propulsive thrust, and you didn't need the wing lift to be enhanced. So all these rotors were turned off, and the props really folded. And so that's another example of autonomous shape change. So here we are looking at autonomous shape change using shape memory alloys. So shape memory alloy is a temperature sensitive material, and the idea is that supposing I'm going to skip this in the interest of time. Supposing I put a shape memory alloy sheet on the underbelly of the blade. Okay, and what I have here is this end is the root end of the blade, this end is the tip end of the blade, and this brown part is the SMA, or the shape memory alloy sheet skin. So this is the morphing part, and somewhere beyond that you have the classical skin. So this is the outboard non-morphing section. This is the inboard morphing section. In this top figure, I've shown that the inboard morphing section goes from the root to 25% span, but it can go to 50, 75, 100, whatever you want, right? And the bottom figure shows what that morphed version might look like. So the spar again is not affected, the outboard part is not affected, and this boundary between the morphing and non-morphing part can be a slit boundary or it can be a continuous boundary. So what we are showing is some performance results. So this is with 25% span morphing, 50% span morphing, and 75% span morphing. The blue bar is the same bar on all three figures, and the first red bar is the same. And what it shows you is the following, that in the cold condition, this is the amount of lift that the aircraft is generating, okay? 21,000 pounds in hover. Now, supposing I increase the temperature, what's going to happen is because of drop in density, my total load, my total lift bearing capability, lift generation capability has dropped, and it's dropped by 2,590 pounds. So I'm going from the blue bar to the first red bar in all three figures, right? Then whether I have 25%, 50%, or 75% span morphing, this shape memory alloy, the question is how much recovery of this lost lift can I get? Okay, so this is the lost lift from the blue bar to the first red bar, and then from the first red bar to the next red bars is the recovery, right? So obviously when I have only 25% span morphing in the inboard section of the blade, not much recovery. 50%, I do a little better. 75%, I do a lot better, right? The first bar is when I have a continuous SMA boundary between the non-morphing and morphing, and the next one is when I have a slit boundary. So for example, if I take a slit boundary, I lost 2590 pounds of lift over here, but then I could recover 2185 pounds of lift, so about 82% of the lost lift. So what happened? What really happened was the following, that this SMA went through a phase transformation. It wanted to contract when the temperature was elevated, and when it contracted, the blade started to camber. So that was the mechanism here. And then we had a follow-up study where we said, okay, in the previous design, there was a lot of strain on the upper surface of the skin. So we wanted to reduce that, and we also wanted to make the core, we had a core in the previous design. We wanted to make it more chordwise compliant. So we said, what if we change the design a little bit? And we basically had this SMA skin, and we started to put in some intermediate spars here. The purpose of the intermediate spars is to support the SMA lower skin. So you can see that when you have no intermediate spars, you were getting about a 13.3 degree camber change with the change in temperature, with the elevation in temperature, which changed the phase from the austenite to martensite. Here, when you put more spars, you get better support, but then, you get a little less camber because there's less active SMA material. And then when you put a lot of spars, the active SMA material starts to become less and less and less, and you go down to about 6 or 7 degrees of camber. Okay, here what we are showing is when you heat this system, the black curve is the change in camber that you get. So this is from, this is the spar end, and here you'll have the tip of the blade, and you can see that the black curve is what you get with heating, and the red curve is what you get with the heating and the aerodynamic load. So you can see that the system is stiff enough that it can withstand the aerodynamic loads, and that the aerodynamic loads are not starting to completely negate the change in camber that you're getting. I'm going to expose you to a next idea, which is reflex camber for reverse flow. When you have edgewise rotors in very high-speed conditions, you have a very large reverse flow region. And this, as you go to an advanced ratio 1, this yellow region will go all the way to the tip. If you go to 1.4, the circle is going to go larger than the retreating side, and you'll have a significant region of reverse flow. Now, in reverse flow, what is happening is the following. This is an airfoil, a conventional airfoil, and you see the flow coming from here. You get a lot of separation along the lower surface. You also get bluff body separation here at the nose, but this is a key contributor to the large drag in reverse flow. So if you start to reflex camber this airfoil, you can start to see that the separation region on the lower surface becomes much more benign. And when you do that, what you get then is this kind of reduction in drag. So this blue curve is for an airfoil in reverse flow, drag coefficient when you don't have any reflex camber, and this red curve is when you have this kind of reflex camber. So significant reduction in drag. So that's one way you can do it. The other way you can do it is you can start to change the airfoil shape. So we started with a classical airfoil here in black, which is used on high-speed, considered on high-speed aircraft. Right? So this classical airfoil will do well in normal conditions, but not so well in reverse conditions, right? So I'm taking this classical airfoil at 6 degrees reverse flow and 6 degrees angle of attack in reverse flow and 9 degrees. And you can say at 6 degrees, the classical airfoil has some separation here. At 9 degrees, that separation becomes much greater. Okay? Now, elliptical airfoils do well in reverse flow. They don't do well in normal flow, but in reverse flow, you see that separation that you were seeing over here and over here is not there. Okay? That's why the drag of an elliptical airfoil in reverse flow is better than what you would have for a conventional airfoil. So what we did over here is we said, what if we change just this lower surface, not the entire airfoil, because, this is all load-bearing, right? And this is load-bearing structure. The less change you make, the better. And most of the effect you can get just by changing the lower surface over here, going from the black to the red. So this is what we call a lower surface modified ellipse. And if we do just that, you can see that these two figures at 6 degrees and 9 degrees angle of attack and reverse flow, you don't get the kind of separation that you were getting for the baseline airfoil, and you get an aerodynamic flow that looks much closer to the elliptical airfoil. Okay? So this was work that we did with Raytheon, and we defined what the curves should be. You start here and you go over here, and they actually built the prototype, and they did a really, really remarkable job. So this was, you don't see the shape change very well over here, but you see it beautifully over here. So this here is the skin. Here, the lower surface skin. This is a normal operation, but then you have these linkage mechanisms. What you're seeing here, the silver is the rib. So we had 2 ribs at the end, and there is a region in between the ribs. And these linkages, when they're deployed, you can see that this lower skin goes from here to here. Okay? So essentially, you went from this black to the red. But I'm going to pose a question now, that when you're in reverse flow, normally, when you're in normal flow, the lower surface experiences pressure. The upper surface experiences suction. But when you are in reverse flow, this part, the lower surface over here, experiences suction. Okay? So the question then is, do I need all these actuation mechanisms, or can I use the change in pressure, the suction that you'll get in reverse flow, to actually deploy the airfoil, right? So I'm putting out some ideas over here because these are directions that I feel are probably worth exploring. Okay, not doing too well on time, so I'm going to try to rush through something over here. If you think of the US Army, they have the UH-60 Black Hawk. This is an 18,300, let's call it a 20,000-pound aircraft, okay? They have the CH-47 Chinook, 50,000-pound aircraft. They have the CH-53 Stallion, 75,000-pound aircraft. So, there are certain discrete assets that they have in their inventory. They don't have an aircraft that's 25,000 pounds or 30,000 pounds, right? They don't have something that's 55,000 pounds. So what happens if you needed a little more than the Black Hawk? What do you do then? What happens is you use the Chinook. So that's what happened in Afghanistan. The Black Hawks could not fly over the mountains in such, in hot conditions at such altitude. So you go to the Chinooks, but you see the Chinook, bare airframe is much, much heavier than the bare airframe of the Black Hawk. So you're carrying all that weight, that empty weight, of a 50,000-pound aircraft to carry those extra 5,000 pounds. So you're carrying more gross weight and you have more drag, right? So if you look at the Black Hawk at 23,000 pounds, this would be the power. This would be the Chinook airframe trying to do the 23,000-pound job, and you can see that you'd be spending so much more power because you're heavier and you're more draggy. So the question then is, can we have, horses for courses type of approach? What if we had the ability to add lifting fans to a Black Hawk or to a Chinook? Obviously this is not happening this is not in-flight morphing, but it's, operating condition to operating condition, that in certain cases I would have this. It's like saying, my blade chord for any helicopter is so much, but if I'm operating on Mount Everest, can I use a different blade, right? Can I use a wide chord blade? So similarly, can I add features to an aircraft when I need to? So here is now, supposing I have a quadcopter in red, right? And it's doing a certain mission, going a certain range, carrying a certain payload. But I need to go further, so I need more battery, or I need to carry more payload. And what if I could add more units, right? So this was an idea that we proposed a long time back, and Boeing worked on it too. They came up with something called the Lift Project, where they said, here, we'll keep adding units, and we'll build an aircraft to meet the mission. We also did something similar here where we said, okay, let's say, what if you start with a quadcopter, right? You need more, so you need to go further or you need to go heavier. You make it into a hex, add 2 rotors, right? Okay, you need to do even more, get rid of those 2, make it into an oct. You want to do even more, make it into into a decacopter. So we actually built it, and this was a quadcopter, and we added 2 booms to turn it into a hex if you needed to do more. And when the booms were added and the contacts were established, the flight controller could tell that we need to use hexacopter controls, not quadcopter controls. I think I'm out of time, so I will wind up with these 2 slides. So challenges and opportunities: system integration, weight, complexity, reliability. This is an issue now. The stiffness versus compliance. That how do you make it stiff to carry load and compliant enough so you're not spending too much actuation force and power? Reconfigurable controls with morphing is another, because a lot of these high-speed aircraft, like compound, they have fixed-wing controls and they have conventional rotor controls. So how do you exploit that? Morphing for additional uses like low noise, and it's important to work with people who understand rotorcraft performance, because there are a lot of people who say, look, I can change the shape of a structure, right, without understanding what is really needed of this aircraft. And then failure modes is another issue that not too many people in the morphing world have looked at in depth. Okay, so more than fixed-wing aircraft, the benefits of morphing, the challenges are greater, but the benefits of morphing for rotary-wing aircraft would be very significant. Flexible skins may be nice, but not critical. Discrete shape change rather than continuous may be adequate. Centrifugal force is the 800-pound gorilla in the room. Exploit RPM change when possible. Do not get too attached, this is my own view, to a specific way to implement a certain type of morphing, right? So if you need to camber, don't say, no, it has to be an electromechanical actuator. Okay? Maybe an SMA is better, maybe an electromechanical, maybe something else is better, right? Do not get too attached to a specific morphing solution for a system level objective. Example, don't say, I need to droop the leading edge. Try to figure out what is it I want to do. I want to push stall out, right? If I want to improve the stall behavior, then compare everything that improves stall behavior, whether it's leading edge droop or gurney flaps or chord extension or whatever you have. So acknowledgements, I want to thank the alumni who worked with me. This is all their work. And I get the joy of presenting it to this group over here. So there's a lot of PhD students who are now at Boeing and Sikorsky, working with the Army, Bell, Joby, various companies. And I have a very strong team right now with 10 PhD students, 2 research scientists. And I wouldn't have done all of this without my sponsors and many useful conversations with so many colleagues and collaborators. So thank you for your attention. I'm sorry for running long, but I'm happy to stay here and take a few questions if you have any.
So I'd like to thank Farhan. As you can probably gather, there's a lot more where that came from. So we have more or less run out of time, but if people would like to ask 1 or 2 questions, there will be an opportunity in a few minutes. But is Laurice here with the microphone? We'll have time for, if you could ask questions via the microphone, we'll do just a couple of questions. So if you could talk into the microphone, would anyone like to ask a question? Yeah, just here.
Thank you, Farhan. This is so interesting. I'm Maria Rivera, teaching fellow at the College, and former graduate of Maryland as well. Lots of tools was all fantastic talk. Thank you. My question is, traditionally conventional helicopters have gone for fixed RPM. Do you think all these today might incline them to move to more variable RPM? I know that more modern unusual configurations are going for 19 months RPM that can change, but what about the conventional helicopters that will follow?
So I think, Karam started that, as almost everybody in this room is aware, because for a long time, the Boeing, Sikorsky's, Bell's, the Augusta Westland, probably Airbus, the legacy OEMs were doing things in a certain way, and for good reason, right? They were trying to avoid resonances, and they said, if the excitation frequency is such and such, how can I design the fuselage to try and minimize different vibration levels? But then I think, once CARM came along, it's not that vibration problems will not be there, but I feel the performance benefits of variable RPM are frankly too great to overlook. And over the last so many years, I would say 15, 20 years, that mindset has changed. I don't think people are now insistent that it has to be a fixed RPM. If you think of any high-speed aircraft, the change is there. The question is how much change, right? But if you're flying 200 knots or 250 knots, you're probably going to slow down the rotor a little bit. If you think of the tilt rotor, right, the hover RPM and the propeller RPM are different, quite substantially different. So, and with eVTOL, they're becoming variable RPM. The thing is, you're going to take advantage of that, and then you're going to deal with a different set of challenges, but it's coming the way I see it.
One more question.
Switches on. Thank you, Professor. That was fantastic. I do a lot of work in the global south with very small drones. We're talking 55 to 100 pounds. And the norm, I think you mentioned it in your closing couple of minutes there, the norm is that we have a quadcopter to get airborne and a fixed wing on it, and we move with one battery array, the quadcopter moves it forward till we get lift from the wing, then we have a pusher prop. We now fly African-built drones 280 kilometres with a 2 kilogram load based on that. This is the biggest improvement I've seen in what we do with small drones in the last 5 years. Your potential and proven improvements, I take it, are for larger rotor wing aircraft. Is this work also being done for the smaller drone community, please?
So, I have seen people do it for small drones. In my personal view, the value of doing this is greatest on expensive assets, right? When you're building something that is worth millions of dollars, okay, you are going to be only able to afford so many of those, and you want those aircraft to do as much as they can for you. If you're going to build something, I'm not putting a price to your drone, but just for the sake of argument, if something costs $25, right, or $250, I can make not 5, but I can make 5,000 of them to do this and that. Why do I need that to morph? So, I've seen a lot of people take these very small aircraft and morph them, and people come up with different solutions. I think the value is at the bigger scale. The greatest value is at a bigger scale. Because I'm showing you the benefits, but there are a lot of challenges. The complexity, the reliability, all of that, it's not a joke. And, I will be the first one to say, don't do morphing because your compromise solution is good enough. Don't do morphing till you get to a point where you cannot afford not to do morphing, right? So supposing if you are thinking about variable twist, right? The optimal twist in hover is different from high-speed forward flight. But if your aircraft was only going to go to 150 knots, maybe the penalty is one that you can absorb. But if you're going to go to 250 knots, maybe the penalty is one that you cannot absorb, right? So you have to consider that cost-benefit analysis.
So, a healthy dose of realism to end with. And what distinguishes Farhan's work is really innovative work, which actually, if Cierva were alive today, this is what he'd be doing. So it's entirely appropriate that you have been talking about this topic. And to end with saying, well, actually, here's a dose of reality as well. It's been a real pleasure to welcome you back to the UK. And it's just, I'd like to thank Farhan again for a truly spectacular lecture. Thank you.
Thank you very much. Thank you all.
Now, we have one final aspect to the evening, which we have a reception to go to upstairs, which has been supported by Leonardo. And I have to say, Leonardo has shown a particular interest in this lecture because actually, for generations, actually, Leonardo have led rotor design in Europe. The innovative work they've been doing on rotors started 30, 40 years ago. So actually, they really wanted Farhan to come over and give this lecture. And I do thank them for supporting really innovative technology for the whole industry. Also, this has been recorded and will be on YouTube, and it is in all of our interests, and I know Leonardo would like us to do this, is to encourage young people to watch the recording because actually it's all very well us in the room, and I'm delighted to see some young people in the audience. We need a lot more of you here. So I encourage you to let other people know this is on the YouTube channel to encourage more people to get involved in our industry. And so finally, I'm sure Farhan will be delighted to answer more questions, but now the rule is you can only ask him a question if he has a glass of wine in his hand. So if we'd like to
This is turning into a drinking game.
No, we won't do that. So if we'd all like to go upstairs and also thank Farhan again. Thank you.
Thank you very much.